So I'll talk a little bit about my postdoc work, what I've been doing for the past year and a half. And it's fairly high level, so if you guys have any questions, feel free to interrupt and just ask me as we go. So yeah, let's jump in. Okay, so my research generally answers the following question. So how can we ensure safety in these data-driven robotic systems that have to operate out in the real world with other people? So to answer this question, we're going to take a very close look at people, really think about new ways we can model and interact with them, and really rely on tools from learning and optimization to come up with these models and control policies that are finally executed based on this sort of foundation in control theory. And all of my work, I firmly believe, has to be proven experimentally as well as just in theory. So all of my work, as much as we can anyways, we actually do out on a real vehicle or in a very realistic test environment. And the big goal of this is hopefully at the end of the day, we can push all of this work out into the real world and really test and make sure that it can operate out with people out on public roads and whatnot. So my domain of expertise is really in the field of autonomy and the vehicle-related work, and it's a really exciting time for this area. So there's a lot of work that's happening both in robotics and in autonomous vehicles, and it's really sort of entering the public consciousness. So these systems are out on the road, people are really talking about them, and there's sort of a lot of hype built up around them. But there's some hesitations behind this. So this article basically highlights how even though there's a lot of research energy going into these fields, there's also a lot of disillusionment. Specifically, this looks at a Volvo study. So they were supposed to release 100 cars into the hands of everyday people to really see sort of how people would interact with their autonomous systems. But they actually delayed this study about 5 years because they weren't able to actually show that their systems were safe, and they weren't able to really understand that interaction with everyday users. I think this really highlights how there is a need to really make sure we have tools and methods for validating these systems that are highly interactive, that are sort of operating at a different scale than anything really has before. And so just to take another sort of mental check, let's look at sort of the state of autonomy. So here is a video of the Google car approaching an intersection and trying to make it through without too much success. So for a point of reference, let's look at how human drivers behave. So this is human drivers at an unstructured intersection. So clearly there's a gap here between sort of state-of-the-art autonomy and human drivers. So one of the questions we try to answer is, how can we close this gap? How can we make autonomous systems more interactive and more human-like? And there we go. Actually, this is great. There's also another one. Yeah. Now, I will admit these are very cherry-picked examples. The Waymo car doesn't always fail at every intersection, and not every intersection, especially in the US, is like this one on the right. But this failure on the point of the autonomous... Actually, I think this is Ethiopia. Yeah. But yeah, there actually are crazier intersections, so this one is sort of reasonable. But even though these are a bit cherry-picked, this failure of the autonomous vehicle is actually fairly representative. So most failures actually come from what we'll call failed interactions. So this is a failure in predicting how other human agents are going to behave, or a misexecution of their own maneuvers. We can also take a look at airplanes and look at the emergence of autonomy in that domain, which has been dealing with this sort of mixed autonomy and introduction of autonomous systems for a lot longer than the vehicle world. So this is one of my favorite plots. Sorry, I think most of you have seen this before. But on this plot, we'll see fatalities per million departures over time. So this is years on the x-axis. So if we look at all aircraft over time, we'll see this nice decaying trend as we're getting safer and safer over time. But if you break it down by generation of aircraft, you'll see a really interesting trend. So the first generation follows the same trend, but each subsequent generation has a spike in fatalities. So what's sort of interesting is when this is first introduced, this actually becomes more dangerous than the previous generation, and it takes about 5 to 10 years to sort of reach this steady state out in the tails. And just so you know I'm not lying to you, here's the real data from Airbus. So you can see even minor changes in the generations of aircraft can lead to pretty significant consequences when they're put into the hands of pilots. So another sort of interesting point here is that this is data from pilots. So these are trained professionals who are trained prior to actually operating these systems. So it sort of raises interesting questions when you have autonomous vehicles that are sort of handed an autonomous vehicle or some level of autonomy. We can only imagine that this sort of trend is actually going to be worse because it has to deal with sort of the higher complexity and the lack of training that comes with everyday people. Okay, so just as a quick snapshot into what the future of autonomy could look like, here's an artist's rendition of what a fully safe, fully autonomous world could look like. So again, this is an artist's rendition, so it's a little played up. But if we have really safe, interactive autonomy, we can really change how efficient our cities run and change how our whole systems are laid out. So there's a lot of room for impact if we can achieve something like this. Although this is totally choreographed, so I think this would be extreme. So my research generally looks at what we'll call human-centered autonomy. So first, a lot of my work that Rujna mentioned was really looking at how to model human drivers that have to interact with a shared or semi-autonomous system. And a lot of my work when I was here was also based on experimental test beds for actually gathering data and testing that these systems work as we expect. More recently, we used a lot of these models that we initially built, just looking at the driver interacting with a single vehicle, and looked at how we can design autonomous systems that both have to operate safely among other human drivers, but really also just looking at how we can design safe systems that stand alone. And more recently, we've also been looking at these sort of chains of interactions, so really thinking about how these works can really expand and extend to multi-agent settings, where you not only have autonomous systems and human drivers, but also other maybe more vulnerable agents like pedestrians or cyclists. So today we're going to be talking about sort of quick looks into each of these areas. So first, we'll look at some of this recent work in autonomous driving. And again, this is going to be sort of a high-level look at what we've been doing over at Stanford. So again, if you have any questions, feel free to interrupt. Then I'll talk a little bit about some of our work here, although I'll probably go pretty quick because I think a number of you have already seen it. And then we'll end in some of our more recent work, actually also in collaboration with some folks here at Berkeley, in how we can connect decision-making and perception in this multi-agent setting. Okay. So since starting at Stanford, I basically was put on this project with a pretty vague goal that was basically to design a system that was both safe and efficient in an urban setting. And urban settings are particularly interesting in the case of autonomous driving, as they typically have lots of different types of agents and lots of high-level decisions to be made. So we sat down and put our thinking caps on, and we asked ourselves, how do we create a safe and effective autonomous vehicle? So we took sort of a standard robotics approach and really broke it down to different, into some sort of hierarchy. So at the lowest level, we implemented a robust MPC. So we have a low-level controller that can safely operate our vehicle as we expect. So this is nice. So as we start playing with some more interesting or advanced decision-making tools, we'll sort of have this sort of safety net that we know we can at least control the vehicle safely using sort of standard control techniques. Building on that, we started thinking about how we can play with this higher-level decision-making systems, and we've been looking at safe imitation learning, so we can look at how people make decisions and try and glean some information and some insight on how people make these decisions in these very complex environments. And then finally, given this whole decision-making pipeline, we've really been looking at how we can rigorously validate our system. So given that you have some decision-making pipeline, how can we find where the system is going to fail and really see how robust this whole pipeline is? And then finally, we want to implement this on our test vehicle, so we have to interface with perception and localization and actually test it out on the road. So today, I'm not going to talk too much about the control, but I'm going to, at a pretty high level, talk about some of our work in imitation learning, so trying to learn directly from human behaviors. Then I'll briefly talk about some of our work in validation, and then show some videos of it actually implemented. Okay, so for safe imitation learning, we basically are operating with this we're operating off of the idea that we want to be able to learn from human drivers so we can smoothly integrate with them on the road. So if an autonomous vehicle is more human-like, we argue that they'll be more understandable and be able to do a little bit more realistic things, kind of like that intersection video that we showed at the beginning. So we've been looking at imitation learning, which is basically where we want to learn directly from human drivers. So we're going to, instead of learning, or it's basically an alternative from reinforcement learning or inverse reinforcement learning, we want to gather data of human driving and glean directly from that experience. So in this work, we're going to... I know. So I'll talk about that in a minute when we talk about what these things actually are. Yeah. Right now I'm just motivating the problem. Yeah. But the basic idea is we're building off of the common Dagger framework, where we basically want to be able to collect data from a human driver and slowly introduce sort of our system to this sort of driving environment. So you can think of this as a novice driver or someone who's learning how to drive being guided by someone who is more like an expert. So in this case, you can think of a semi-autonomous system that slowly learns how to drive from its human sort of guiding it, and eventually it will be able to take full control and guide the full system. So in this case, so you can think of basically your environment as your world, and your observations are going to be your states and some information from your perception. This is going to come into both your novice, which will be basically your decision-making policy that you're trying to train, and as well as our expert. So in the case of a human driver, they observe the world with their eyes, that's their observation, and they're going to output some action, so maybe a steering command to the vehicle. So basically in this online framework, what we're going to do is we're going to introduce this decision rule that's basically going to balance exploration and exploitation between letting the driver be in control and learning how to safely drive from that driver, and then letting basically our novice or this uncertain policy that we're training have more control. So when we let this new policy or this novice take control, we're going to get new samples that maybe the driver wouldn't see. So let's look at a very simple example like this inverted pendulum. So in this case, our observations are going to be the state variable, so basically the position. So here we can visualize the position here and the angular velocity here. So for this relatively simple system, we can visualize the safe set, and that's these purple dots here. So this is basically the basin of stability. So any initial state from this purple dot area can be guided to basically standing up straight, so to this origin. This is just a simple example on this guy, so an inverted pendulum. This is a simple example. I'm just trying to visualize it. It's hard to visualize the state space of a car. So in this case, OT is the state space, so it's going to be the position and angular velocity here. Okay? So basically, given a state, we want to guide it to 0. Yes?
On the left-hand side, where is the expert policy coming from?
Next thing I was going to say. So in this case, we're just using a standard nonlinear controller. So basically, you can linearize your system, and it will bring it back to 0. So this is using standing control techniques. It's an example in Khalil, actually.
But in a car example, I guess you'll get there.
Yeah. So in this simple case, we have our basin of stability in different places where we know we have a controller that can guide our system to equilibrium. So to it's basically standing up straight, stably. So what we want to do is we want to test out our framework on this really simple case so we can just get some idea of how it's working. So in this case, we're going to basically collect an example trajectory. So that's going to be this red line of our expert, or in this case, our nonlinear controller, that is able to stabilize our system. And we're going to iteratively collect more data and assess when our novice is able to bring this system to equilibrium. So here we take basically a step through this algorithm. We're going to see when this novice actually can bring the system to equilibrium. So these black dots show basically our new policies, basically basin of stability. So these are the states at which it can also stabilize the system. And as we collect more and more data, we're going to continue this, grow this set within the basin of stability of our original controller. And eventually this is going to grow and grow and we'll collect more data, and hopefully we'll have the same basically performance and robustness of our original controller. And in this case, it's a pretty simple example. So this is just a toy showing how we can basically grow our set. And also, this works in the case where we have a good model of our system, and we know exactly sort of where the limits or where the safety is well defined. But in more general systems, this is often really hard. So we're going to approximate this novice as a Gaussian process so we can get some measure of confidence. And they'll basically allow us to not decide based on strict rules of stability or safety there, but an approximate with probability arguments. So we can now say with high probability, we can also stabilize the system. And we'll talk about some of the consequences of high probability and safety in a moment. So just as another visualization of what's going on, so this is our expert controller. So again, this is the nonlinear controller that's able to stabilize our system and bring it to equilibrium. And I think it cuts out a little early, but it does stabilize our system. If you were to just take some data from this and try and train a policy based on this, you'd often fail quite poorly. But with this sort of training paradigm, where we are now making decisions based on our perceived confidence of the novice, we can now have a new training method where we get corrective actions from our expert. So here we're basically switching between our known controller and our novice, and we can basically get these corrective actions here. And then at the end of the day, we're able to get a novice policy that can more efficiently stabilize our system. Yeah?
So are you essentially applying the expert at the boundary of your confidence on the system?
Mm-hmm. Yeah. So this is just a pretty simple example. And we did this for pretty simple systems and in simulation, but actually just last week we started doing this on a car. Oh, yeah?
Really quick question. If you have the expert, why don't you just use the expert all the time?
That's a great question. Okay. So I had a slide before, but there are some cases where you maybe don't want to use or directly query your expert. So this might be when it's either really expensive or operates maybe on really expensive sensor measurements. So maybe you have an expert that operates on LiDAR data, but you want to be able to control your car with just maybe camera data. So you can actually use this to transfer from one very difficult system, but that works really well, to a maybe more complex, maybe more noisy, but similar system. So there's that. And also in this case, you have a nice policy that's easily parameterized. Like you'd never want to use this method on a pendulum in practice. But if I had a human that was driving and I wanted to mimic that human, I can't directly parameterize that easily. So this is basically a method for learning that over time. Yeah. Yeah.
You mentioned Gaussian processes before. You're going to go into more detail there?
I'm not. This is a high level.
Can you kind of like explain that idea?
Yeah. So basically, we're using an approximate Gaussian policy or process to do this policy. But basically, the idea is at every step we get both a mean action as well as a variance. And that variance has been shown to be very related to a metric of familiarity. So the basic idea is when you go to a very unfamiliar state or something that you've never seen before, you're going to have a very high uncertainty in that output. And that basically gives you some approximation of what your confidence will be in those states.
Can I rephrase really quick?
Yes.
So is it basically saying if I've seen a sample of the expert telling me what to do here, I trust that my GP has learned the right thing?
Yes. Yeah. So that is another assumption.
Just to understand that situation, so the expert is trying to swing up the pendulum, is that what you're saying? Mm-hmm. So it's outside the domain of the stability. And why are there two of them? One left hand and one right hand?
So this is the expert that is stabilizing the system here. So
Two of them.
Oh, this is a bunch of initializations that are all converging. Yeah.
And the online training doesn't make it work?
This does. So the naive novice, so it went this way. So it went expert, naive novice doesn't. Online training helps, and then you get this. It's sort of a snake there.
What are the decision rules? Like, what are the specific decision rules?
So in this case, we were looking at basically if we have a confidence set. So here this is defined by basically the variance that we get from our novice here, because it's a Gaussian process. We're able to basically see where it's confident and where it's not by looking at the variance of our system over the state space. And whenever we hit this boundary, we basically say our novice is not familiar with this state space. We're going to pass control back to our expert.
And if the
So in this case, it's the full state space because it's a relatively simple system. When we're doing things on the car, we're not doing the full states. We're just basically doing some subset of them. And if there are no other questions, So on the car, so this is the next picture. We were running experiments on Friday on the car. And in this case, we were looking at position, speed, heading, and then perception information of obstacles around it, of the vehicle. So we were collecting data from a driver on the car and testing it in a pretty simple environment. So in this case, no. Yeah. So again, we were just doing these experiments just last week, so I don't have any great slides on them. But one of the kind of cool things is we can visualize this uncertainty over the reachable space. So this, again, sorry, it's not super pretty. They're new. But this is basically different points where the car is starting here, the reachable set is extending out. And we can look at basically how well or where the novice is confident in the system. So these are for different thresholds on that safety. And one of the kind of cool things is when we're working with humans, we can sort of see where, get different levels of uncertainty on where they're deeming things unsafe. So because we're working directly with a human, we're able to learn a good threshold online, which is typically very difficult. And one of the things that's sort of interesting is this is an example of a very high threshold that isn't very meaningful. So this is basically everything is safe and everything's okay. We can also look at a other threshold that is very low. That means almost everything is dangerous. But one of kind of the cool things of working with this human online is we can learn a threshold that is sort of meaningful. So we can basically get this clear space, which is this blue space here. So we can kind of learn where safe spaces and where dangerous areas are on the road. Yeah.
There's a point of view which says that human learning is a feed-forward component and a feedback component. It seems to me that you're only learning the feedbacking component. I mean, for instance, a lot of driving is a open loop trajectory where you don't loop. And there's feedback on the basis of, by the way, there was a talk right before this, so we're also with a completely feedbacking strategy. So how come people have lost interest in the look ahead part of the controller?
That's a great question, and I don't think I know exactly the answer to that, but that's a great idea. Maybe next things we can do that.
About your pendulum being a swing-up pendulum. Swinging up the pendulum, you have to think about sort of the plan ahead part, which is a strategy to swing up, and then stabilization.
Yeah.
The question is,
No. You're right, and this is very sort of one step. So this doesn't really take into account long planning. And one of the downsides of this, you do have to sort of specify the task and what you're doing sort of before you do any of this. So I think that is one of the downsides of this approach too. Yeah.
Can you say a little bit about what you mean by safety in these two contexts? So it seems like there was stability in one case, and I'm not entirely clear about safety in this case.
So in this case, we're basically just, so this is looking at that uncertainty metric again. So we're basically just sort of trying to, this is under the assumption that there is a relationship between the novice variance, so this basically uncertainty in the policy, and there's sort of unsafe regions in the real world. So that is one of the assumptions that we're making, is if you watch a driver drive, you almost never see them go off the road, so it's quite likely that off the road is someplace you don't want to go. So that is one of the assumptions that's being made here.
Right, but just to make sure I understand, so if there's like oncoming traffic in an intersection, presumably that's like a less safe, it's a harder situation to be. So would you expect that your expert would show different maneuvers in that place that would show you higher variance or something like that? Or
yes.
It's less safe?
Yeah, so in this one, so I guess this kind of builds off of what I was just saying, that you do have to be very task specific in this, and this doesn't quite generalize to many different settings. Although if you encountered a situation that was very different than what you previously had seen, that would flag this sort of, or be a very high uncertainty or very low confidence region. Yeah.
For generating these plots, you're showing the reachable set, assuming you're starting in a certain state and looking forward, but then you get the red or blue by, okay, if I were in this state, what action would I take and then looking at?
Yeah. So it's basically just querying along this.
So it's not showing like an action plan from that initial state and then.
No. Yeah. Yes? So you can't really see, maybe you can kind of see on this top one, but there actually are obstacles here. So again, these are brand new plots, so they're not perfect. But yeah, so there are actually obstacles in the road. And so the action that we're actually learning is this weaving maneuver. So here, we're spoofing our sensors. So we're not actually putting real cars out, but the car thinks there are cars where these cones are, and we're learning a tight weaving cast. So we're basically operating like this through the road. So this is just an example of how learning from this human also gives us some insight to sort of what different thresholds are meaningful in this context. Yeah?
Just quick clarification. The 3 different reachable sets are like over time when it's learned?
So it's the same thing. This is basically just barring different thresholds. So basically the blue is the sort of safe space. So it's the same thing, just different sort of level sets of it.
Oh, okay. Mm-hmm. And when you said that it's safer in the Gaussian process sense of when it's already seen something from that particular state.
Mm-hmm.
So why does it, when you go off the road, does it feel confident in what it should do?
Yeah, so there are a few things here. So it's not perfect. And this is just making probability arguments here. So there are lots of questions on if you're making a probability argument on safety, is it really safe? And we'll talk about that in a little bit after this. But yeah, that is one of the problems, that it is still a little loose, but it's basically a somewhat principled way to find sort of a safe set. Yeah. And again, this isn't really taking into any known information. Like in this case, if we're operating on a car and operating in a road, we could probably predefine a lot of these. But this is more of just an example of what you can do. Yeah.
So like the case that I've always kind of had in my head when the GPs kind of brain for this sort of thing is when there's like a bimodal distribution. Like I can go around the corner, I can go right or I can go left.
Yeah.
So how does that kind of work here?
One of the assumptions we make is that it's unimodal. So yeah, that is one of the things. I put up a warning. This was a high-level part. Yeah. It's okay. Yeah, so this was just a simple example. But there are some approaches to extend to looking at different modes in distribution. So there are like ensemble methods where you can look more at sort of multimodal settings. Yeah. Okay. So as I said, this is kind of nice because we get some nice intuition about things and we can show some pretty good performance overall. But when we're thinking about validation, that's not really, probability arguments aren't always that useful. So we started investigating vigorous validation. So and we're going to use a tool called adaptive stress testing. And one of the kind of interesting things about the autonomous car setting is that you have this sort of interesting thing where you have very high risk states or failures, but they're at a very low probability. So if you look at the disengagement rates of current autonomous vehicles, so you get 0.12 per 1,000 kilometers. But if you look at human driving, you have a really, really low collision rate. So to get a meaningful sample or to really show that your system is better than a human driver, you're going to have to drive for hundreds of millions of kilometers of miles just to get an example of a failure. So to solve this, a lot of people turn to simulation. But even if you're just blindly simulating your system, it's still going to take a lot of computational power, and it's not exactly easy to find where your system is going to fail. So we've turned to this idea called adaptive stress testing, and it's basically a tool that we're using where we're going to actively search our system to find where your system will fail. So this is a black box optimization technique. So basically, we're going to control our simulation and guide our search towards the most likely set of failures. And we're going to do this through Monte Carlo tree search, and we're going to provide it a reward section, or a reward function, that basically tries to incentivize decisions that are more likely, but also reach a failure by the end of some time. And what's kind of cool is this is a black box simulation. So if you have a simulation of your system, you can apply this as a wrapper around it and sort of search for where your system is going to fail. So you're basically returned an example of how your system fails, as well as a probability of that failure. So as just a little example here, so here we're going to look at a simple T intersection. So here we're going to look at just some nominal decision-making policy, and we're going to be this car here. Sorry, the colors are a little funky. But here we're just trying to make a left turn through this intersection. So if we take some nominal policy and we just simulate it for hours and hours, we can basically decide when it's safe and execute this left turn. And if we simulate this for hours and hours, we're not going to find a failure. But unfortunately, we know that there are likely bugs in our system and that this actually isn't going to work in practice.
Can I just ask a
Yeah.
question? I didn't catch what's changing in each iteration of your model.
So in this case, so there are a few different ways to actually implement it, but in this case we're controlling the random seed that controls your entire simulation. So the output is basically the sequence of random seeds that then gives you a trajectory of your system.
So what information is captured in this?
So basically this random seed controls all of the randomness and all the uncertainty that's present in your simulation.
Like where have you situated that? Like where is the random here? In the initial positions or?
Yeah. So it sort of depends on what your test case is. In this case here, we're basically controlling some variability or some noise on the actions of these vehicles. So you'll see what the failure is, and it's a pretty simple failure. So in this case, the car's paused, they show some hesitation, and the car's convinced it's going to go, and it fails. So it's just this sort of scenario that it's never been seen before, or it's never seen before, but wasn't really in that decision-making logic. But that decision, or where that uncertainty comes in, is sort of up to that simulation. Yes?
What's the simulation model?
In this case, do you mean just this simulation here?
What sort of a model is it? Is the entire system model as some kind of an MTP where or each agent is an MTP and it is product?
So the outer wrapper,
This relates to, I think, Claire's question of where's the randomness, the seed, where does the seed get used?
yeah, so in this case, this whole thing is sort of modeled as a simulation state, and that simulation state is treated sort of as a state in an MDP. And that sim input, basically whatever uncertainties that you're allowing in your simulation will be controlled by this random seed.
So you have a bag of actions and then you can each have an associated probability that depends on.
Yeah, and that's defined by whatever's in your simulation. So in our simulation, we basically are looking at very specific agent models that have transition probabilities, and that's where that.
Agent, what kind of probabilities?
So the transition probabilities, it's basically, so these examples here, so each of these cars is given a goal, basically a goal target point, and then they're run by a standard driver model used for simulation. And then the uncertainty basically, so it's guided by this dynamics model that models human behavior, and then the uncertainty basically just comes from some random process or some noise that's added to the actions there.
I mean, you use model of human, model of car, what are they? I mean, it sounds like mystery.
Yeah. So these are run by IDMs, but the thing that's supposed to be nice about this is it works on a black box simulator. So in this case, we're running a very specific simulation, but in general, you can run it on many different simulations. Yeah. Okay. And since we're running low on time, I'll quickly go through. So basically, one of the big questions is, what do you do once you have this information? So we've been looking at adversarial settings that build off some ideas of adaptive control to basically take these likely failures and incorporate it into your system. I'll go very quickly. Sorry. We are both safer and have a higher success rate by using this. I'll skip some of these videos. And at the end of the day, we want to put it on a vehicle. So here we have our LiDAR information. So again, we're not touching any of the perception that's provided by our sponsor. So they basically provide us an object list that then comes into our decision making. Here, we're approaching a stop sign here. It's a little hard to see, but there are two cars at the intersection, so you can kind of see them from above here and here. And we're going to make a decision and go through the intersection. Now,
What do we see from the top left?
the top left. So this is the LiDAR information overlaid with the map. Yeah. We've also looked at other things. So here's an example of a lane change. Let's see, is it going? Yeah. So basically, this is just showing that we can handle sort of multi-agent settings. So even though this is a pretty simple maneuver, lane changes are very hard to actually execute in practice. So we're able to safely execute such maneuvers. And at the end of the day, these are just some examples, but we're doing basically a full loop of urban driving settings. Okay, so that was a quick overview of some of the work that we've been working on in this autonomous driving systems. So let's see. I will go very quickly over some of the stuff that I did here at Berkeley, because I think a lot of you guys have seen it before, but again, if you guys have questions, let me know. And then hopefully I'll have time to talk about some of this more recent work, since that's with some people here. Okay, so as you know, when I was here, I was working on driver modeling, and I was working with this giant machine. So I was collecting driver data on this driver simulator. So we can actually collect user data, see how they're going to act, and design controllers that can then keep them safe, or autonomous systems that can interact safely with them and actually test them. So this is a little more exciting than everyday driving, but I think a lot of you guys have driven on it, so you guys get the idea. Okay, the other thing that's nice is we can actually collect all this driver monitoring data, so we can observe the human driver, and we can do things like see when they're distracted, and we can safely sort of put them in scenarios that might be dangerous. And we can also collect a lot of other sort of observable information about that driver's state. So we can look at the motion capture system to get their pose and see how they're physically interacting with the vehicle. We can also use eye tracking to see where their attention is. And we can do things like affective sensing to try and model some of their more physiological states as well. And while I was here, we looked at a lot of different applications. So first, we looked at the shared control and active safety. So using these models of driver behavior to basically keep the driver safe, depending on what they were likely to do. Then we used some of these models and showed that we can actually use the same ideas and principles and do it in a more interactive case. So if an autonomous system is going to interact with a human-driven vehicle, how can we ensure that there's going to be safe interaction? And we can also use these models for sort of offline assessment to see when and where they're going to fail. So again, the primary motivation here was this idea of active safety. So the big question here was, if we can identify the driver's state and effectively predict their likely behavior, can we design better, less invasive active safety systems? So again, we're going to watch the driver, and in this case, we were basically pushing them into sort of dangerous scenarios, so we had them texting while driving. We wanted to come up with some sort of driver prediction, and this was building off of this idea of reachability. So we wanted to basically see where likely trajectories were going to take them. And we wanted to design an intervention function. So basically decide when we should have some sort of intervention or something that should intervene to keep them safe. And the big intervention here, we had a model predictive controller that was always operating that could basically be that corrective agent when the driver needed it. So the idea here is we're going to augment that driver and keep them safe, but only when necessary. So in the realm of predictive modeling, there are sort of two classes that you can consider. So the first idea is informative models. So in informative models, you can think of this as the exact trajectory of the vehicle. So ideally, you'd be able to know exactly where the person is going to go, basically know exactly what their future state information is going to be. But in practice, it's almost impossible to know this, and it's very, very unlikely that you'll be able to learn a model that's good enough to use in practice. So you can add some uncertainty and add some variability around it, but you still need to have this very good estimate of what their future trajectory is going to be. On the other hand, there's this idea of robust models. So in this case, there's this idea of reachability, which many of you are working on, but this basically is a set-based approach that puts physical bounds, given the physical dynamics of your system, on where it can go. So this is nice because this gives you 100% accuracy if your model is correct. But if you look farther out in time, or you increase your disturbance models, you're going to eventually always be violating constraints. So like in this case, you can kind of see this as we grow this set out, it's basically going more and more towards the edges of the road. So it's becoming very over-conservative. So one of the things that we try to do in this work is to basically shrink these sets down and find a balance between being more informative, so shrinking that set down so it's more precise, but still maintaining this accuracy that you get from more set-based predictions. So we're going to approximate the stochastic reachability with what we call the empirical reachable set. And the basic idea here is we want to maximize precision. So again, we want to shrink this down to something that's meaningful, subject to accuracy. So we formally define this, and I'll kind of skip through these different things. But we basically define this as the Lemaitre measure over the set. So we basically look at the size of the set or area, subject to some probability. So again, we only want to capture some likely behaviors, so we're not going over conservative or finding the really extreme cases. And we're going to do this from a data-driven way. So I'm going to kind of go through this quite quickly. So here, since we're working with a fixed data set, we can redefine this probability as the empirical probability distribution and basically assess how many of these trajectories from our data set that we collected in our driver simulator are actually captured by this prediction delta. So I'm going to skip over this, but we formulate this as a mixed integer linear program. So we basically can identify and capture these sets in a meaningful way. And here's a quick example of what this looks like. So here we have our data set. There are some extreme cases and some outliers. These get set in different bounded sets with different probability thresholds. And we can carry this out so we can get a distribution over trajectory sets. And what's kind of interesting is depending on the distribution underlying the data, underlying the different behaviors, you get very different sort of area profiles here. So basically, at some point, you just sort of reach in and sort of squeeze in on what a more typical set is, so you can really get a really good approximation of what typical behaviors are. This is a very hard problem to solve, since we're working with mixed integer programs. So in this case, you'll have to solve something like 2 to the n optimization programs, which in general is way too many. But there's some nice properties of this sort of sets that allow you to search much fewer combinations. So using this branch and bound approach, you get much better computation time than traditional or naive approaches. But one of the kind of interesting things we noticed was that as you get deeper and deeper into this set, is you have really, really high computation costs still. So one of the kind of cool things we found was that there's this nice monotonicity property if your data is unimodal, and it allows you to much more efficiently compute these sets. So if you have this assumption of unimodality, you can solve this greedily or iteratively solve it, and you get more linear computation times instead of this sort of exponential computation performance. So now that you have a great idea of what this model is, we applied this to driver some lane changing data. So we collected a bunch of data of drivers executing lane changes in relatively complex settings. And we learned different set predictions based on these detected driver modes. And we have pretty high accuracy. And again, there are many different applications that we tested out. So again, as I mentioned before, we applied this to a shared control setting. So we could only intervene when we thought that the driver was going to do something basically bad. So when they were going to violate some constraints that we predicted in our model. We also applied this to some interactive modeling. So the big question here is if we can predict likely driver responses in cooperative maneuvers, can we design an autonomous system that can effectively integrate with human drivers? So here we looked at this case of lane changing and lane keeping again. And we found that if we use this prediction and design a controller based on that, yeah.
Real quick question about, last slide you talked about monotonicity as being an important, unimodality implying monotonicity. In a lane change, it seems like there's often like multiple good options, I would think, right? Like stay in my lane or make a turn.
So that was one of the things. So those detected driver modes basically split it up into a lane keeping and lane changing, and that separated out the modes.
Okay. So
Yeah.
It's like a separate part of the algorithm, you say.
Yeah. Yeah. So basically the inputs have to be these different sort of modes of behavior that you do have to assume. So some of the work we did was on detecting those different changes.
Oh, I see.
Yeah, sorry, I'm now in speed mode,
No worries.
doing a speed run. So basically, we use this prediction method as constraints in a planner, and we're able to show that you can effectively plan or predict likely merging responses using this method. If you incorporate this, you get very human-like motion. So it seemed to capture a lot of the decision-making that people typically exhibit. And we tested this in our controllers. So we had people sit in an autonomous vehicle. And we showed that this increased predictability. So people were able to understand the intent of the autonomous controller at a much higher rate than sort of standard control techniques. Okay. And in my last few minutes, I will just show this video since it's sort of fun. Some of the more recent work I've been looking at is looking at intersections and looking at pedestrian interaction, which is a very sensitive case. So often there are occluded things that happen here, and we want to sort of capture some of the intuition that drivers get to predict these different occluded environments. So usually people can infer that pedestrians are present, and we want to sort of give autonomous vehicles the same intuition using driver models. So I will just very quickly show this video of it working. So this is work with Dapo, actually, in Shankar's group. So by building on these idea of driver models, we can incorporate this into mapping frameworks. So we can basically observe this vehicle and predict and estimate the appearance of different pedestrians. Let's see, it'll shift over in a minute. So just by observing a driver, we can make inferences about occluded regions and integrate this into standard mapping techniques. The other kind of nice thing is, since this is now a mapping framework, you can apply pretty simple sensor fusion algorithms to extend this to multi-agent settings. So now you can look at many agents interacting, and if you have a reasonable model for these different types of agents, you can start incorporating many different things. So you have a really nice scaling in terms of how many agents you consider. But this is just a mapping or awareness book, so now we're looking into how to integrate it into decision making. I'll just skip over these things. This is the work I do. Thanks, everyone. And this is what I talked about. Thank you.